So finally, we are going to start talking about how to find the optimal solution for the transportation problem. I'm going to start by introducing the way to find the BFS, or basic feasible solution. If you recall the linear programming topic that we have talked about in Operations Research 1 course, if we have a problem with m constraints and n variables, where n is larger than m, then we may find the basic solution for this problem by setting n minus m variables equals 0 and just solve for the remaining m variables. So we will have m basic variables. So the point here is that in the basic variables, we have the number of variables that is the same with the number of constraints that we have. And furthermore, if the value for all basic variables are non-negative, it means that we have a basic feasible solution, or a BFS. If we have a transportation problem with m supply points and n demand points, then we may have m plus n constraints, right? Because we have m constraints for the supply and then n constraints for the demand points, so that we have m plus n equality constraints. Now, if we have a balanced transportation problem, then we may omit any one of the constraints, which means that if you have a balanced transportation problem and you have a solution that satisfies the demand for first city, second city, third city, and fourth city, and it also satisfies the supply from the second plant and the supply from the third plant, then the remaining one, this constraint for plant 1, will automatically be satisfied. Or in other words, we can just omit this constraints here and only considers the m plus n minus 1 constraints. So because we only need to consider m plus n minus 1 constraints, it means that in our basic feasible solution, or BFS, we only need to have m plus n minus 1 basic variables. So from the previous slide, we know that in order to find a BFS, we need m plus n minus 1 basic variables. Unfortunately, we cannot simply assign any of this m plus n minus 1 as basic variables. So for example, here we have the example of 2 supply points and 3 demand points. So we need to set 2 plus 3 minus 1, which is 4. So we need to set 4 out of this 6 decision variables, or 6 cells, as the basic variables. However, we cannot simply just randomly assign 4 out of those 6, because when we do not assign it properly, then we do not get a basic feasible solution. So let's see what is the other requirement other than just the number of the basic variables must be m plus n minus 1. Apparently, in order to have a basic feasible solution in a balanced transportation problem, we need to have not only m plus n minus 1 basic variables, but we also need to make sure that it contains no loop. So what is this loop? Well, we're going to see it very soon in the next slide. Here's the definition of the loop. Any 2 consecutive cells lie in the same row or same column. No 3 consecutive cells in the same row or column. The last cell in the sequence is the same as the row or the column that is the same with the first cell in the sequence. If these 3 requirements are satisfied, then we have a loop. And if we have a loop, then we do not have a basic feasible solution. So remember that to have a basic feasible solution, we do not want to have a loop. Now let's check if we have a sequence of 4 different cells or more, and let's check if this is a loop or not. The first one is a loop because any 2 consecutive cells they always lie in the same row, or these two, they're always in the same column. These two, they are in the same row, and these two, they're in the same column. Okay, so the first one is check. The second one, no, 3 consecutive cells. Okay, you don't see any 3 consecutive cells either in the same row or same column. Check. The last cell in the sequence has a row or column in common with the first cell. So again, it's satisfied because let's say if you start here and then you go there and then the last cell will become that, it is the same column. Wherever you start, the last cell will have the same either row or column with the first cell. Okay, let me try again. If you start here, then let's say you go this way, that way, and then the end has the same column with the first one where you started. So again, this is check. So this is a loop. For the second one, again, let's check any 2 consecutive cells, they always in the same row, or any 2 consecutive cells, they always in the same column. So the first one is check. We don't have 3 consecutive cells in the same column or row, so check. And then the last cell in the sequence has a row or column in common with the first in the sequence. So again, if you check, let's say you start here, and then you go there, 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 and then you will end up in the same row. So this is again a loop because you can try that wherever you start, you will end at the cell that has either the same row or the same column with the one that you started at first. And this one is not a loop because if you take these 2 consecutive cells here, so this cell and that cell, you can see they do not lie in the same row or same column. So if any of these 3 requirements is violated, then the answer is that this sequence is not a loop. So the last example here is also not a loop because you can see this cell, and that cell, they lie in the same row, which is the first row here. So again, this does not contain a loop because it violates the second requirement for being a loop. Okay, so these 2 examples, they form a loop, the sequences of cells, and these 2 sequences, they don't form loops. So in a balanced transportation problem with M supply points and N demand points, if we want to have a BFS, basic feasible solution, there are 2 requirements. The first requirement is that we need to have M plus N minus 1 basic variable. And the second one is that the cells corresponding to these variables, they must contain no loop. So the first requirement is M plus N minus 1 variables. The second one is that they contain no loop. Fortunately, there are 3 methods that will help us to obtain this M plus N minus 1 basic variables, and they also guarantee that they will have no loop. These 3 methods are called Norwest corner, minimum cost, and Vogel's method. What I would like to emphasize here is that none of this method guarantees optimal solution. Again, none of them. Because the purpose of these 3 methods is simply finding basic feasible solutions. So these 3 methods, the purpose is only finding feasible solutions. They don't guarantee optimal solution, and that's not the purpose of these 3 methods anyway. Okay, let me emphasize once more that these 3 methods only helps us finding BFS. They never guarantees optimal solution. Okay, so in the next video we will start looking at the first method, which is called the northwest corner method. So see you on the next one, and